So, so there's a bit more counting involved that I want to go over. Um, so I'm gonna call this more counting techniques. And I just want to say that I remember last time we spent a significant amount of time going over some problems from the homework, right? And I just want to stress the fact that mathematics is learned by doing, quote unquote, doing or solving problems. So it's not a waste of time going over homework problems per se, because we're going over problems. And most of these, especially in this class with probability, the more problems you go over, the better and the more intuitive the techniques and the concepts become. So that's really how even mathematics is learned or discovered or invented, whichever way you envision it. It's through problems. Calculus was came up out of trying to figure out the problem of motion, and a lot of times that's what happens. There's a problem and there's has to be a way to solve it, and then people who are creative and ingenious enough find ways, and mathematics is grown. That's kind of a driving force for mathematics. It's solving problems. Okay, so more counting techniques. So one of them is called committee forming, and I think most of you already know what's expected from this. So this is when you want to find ways to create groups. So we already know how to create a group, find a number of ways to create a group, and that's through combinations. But then what happens when it becomes plural? When you have more than one committee that you're trying to create. So something like this, right? An example, and your homework problems are a bit more, they have problems like these. There are 30 men and 40 women in a town library club. They wish to form a committee with 3 men whoops, 3 men and 4 women. And then the question naturally becomes, in how many ways or how many committees can be formed? So how many ways can it be formed, right? So then how do you go about this? You kind of, so I like creating these like blank slots. And so it just helps me visualize my my problem and what I'm expected to do. So I'm expected to do 2 things. I'm expected to select 3 men and select 4 women. I have 30 men to choose from, and I want only 3 of them. I have 40 women to choose from, and I only want 4 of them. And I want to know what's the total number of ways that I can do such a thing. So I can say that this is number of ways to choose 3 out of 30 men. And this is the number of ways to choose 4 out of 40 women. And this becomes hopefully quite straightforward. We have 30, choose 3. And then we have multiplied by 40, choose 4. Okay, this is a dot indicating multiplication, right? Because we're multiplying the number of ways of doing one thing followed by the number of ways of doing another thing. And that's using the principle of counting, or the fundamental principle of counting, which we talked about. And so for these are kind of big numbers, 30, and then you do the factorial of that, it gets kind of big. So you can use your calculator for that. And 30 choose 3, if you compute it, is 4,060. And then when you compute 40 choose 4, you get 91,390. So how many different committees can be formed if you have 30 men and 40 women, and you want 3 men and you want 4 women? How many ways are there? Well, when you multiply them, you get 371,043,400 committees. It's quite a number, right? But the idea is how we get there. That's the most important thing. How are we able to do that? So now we're using our concept of combinations, and now including more events that are associated with combinations. We're not only concerned with finding the combination or number of ways to select a group for one thing. Now we're doing multiple things here, 2 things. And then we can extend this to 3, 4, and so on. Okay. Then the next thing that pops up in your homework, and I think I discussed that in one of the 2 recordings that I was speaking about, and it's called complementary. This is a very important technique, complementary counting. And again, I'm going to stress the word complement. It's not the compliment that you give the people. Complement. And it's not complementary angles. We're not talking about angles that add up to 90 degrees. So the complement in set theory, right? Though the complement of a set. So I should specify that as a definition. So the complement of a set. So I should write this in. So a set, let me just briefly say what a set is, even though some may already know what this. A set is a collection of things, objects. It's a group. It's just any collection of things. So the complement of a set is the set that contains or I should say that does not sorry, I should specify this a bit more. It's a set that contains the things, or I should say the objects, and I should specify it's all the objects not found in the set that one is referring to. So the mathematics can be quite abstract, and usually that's kind of, I should say, one of the drawbacks sometimes of teaching mathematics in a certain way, because we become so dependent upon definitions, and sometimes, and that's where the examples come in. So if we only present mathematics using examples, it can become very long-winded. If we only talk about the abstract notion of mathematics, then people lose sense of what we're speaking of. That's why you need both. You need the theory and the application together. So what am I saying about this, right? So simple example, right? You're rolling a die. Rolling a die, a 6-sided die. Okay. And you create a set. So let set A be the set of when you roll at least a 3. So we usually define sets with capital letters, and I just created a set. The set is called A, and we use curly braces, right, to indicate what the set is inside, what's inside the set. So I'm specifying that set A is the event that when I roll a die, I roll at least a 3. So these words become very important. So the word at least means it could be 3 or higher, right? So that's what that word at least means. And that's going to be crucial to understand. Now, what's another way I can specify A? I can write it in words, or I can actually write out what A is, right? So 3 is in A because it's at least a 3, so on and so forth. 4, 5, and a 6. So that's the set A that I created out of this, what's called a probability, what can be called a probability experiment, or an experiment, or an event. The event is that I roll a 6-sided die. That's my event. And now I'm specifying the outcomes. So let me write that out. So the event is rolling, right? I should just put this is the event. And then what are the set of outcomes, right? This is the set of outcomes. So I have an event and have a set of outcomes, and I specify the set of outcomes. 3, 4, 5, 6. Now, what's the complement of A? What would be the complement of A? And how would I denote that? Instead of writing complement of A, complement, right? We like using shorthand notation. That's what mathematics does. So that's why it makes sense, right? Alexandra, 1 and 2. What's not in A? And yeah, the notation varies, I would say. Some people use the bar over it, but the more, I think, common way is to write it this way. A, and then you have a superscript to the right, and we call it C for the complement. So the C is what? Complement of A is the set of rolling. It's kind of like saying not A. So I should write it like this. Everything not in A. So what is everything not in A? It means that you're not at least a 3. So it's like saying rolling not at least. And I know the grammar here is not the greatest. I'm trying to emphasize the not part. It's not at least a 3. So when you say not, you're implying the opposite, right? So what is the opposite? What is the opposite? So that's another way to consider complement. It's the opposite. So what's the direct opposite is less than 3. Exactly. That's exactly right. So it's less than 3. So when you're less than 3, you're considering 1 and 2. So this is the complement, all right? And sometimes finding the complement is easier than finding what you're looking for directly. And I also specify that in the recording about the example, how I solved it. And I solved the problem in 2 different ways. One way is going through casework, which is creating the cases and then building up and then counting everything. And the other way is to figure out the opposite of what I'm looking for. And then I am subtracting away from the total. And we're going to talk about this idea of the total number of events. And that's what's called a sample space. And that's kind of like, I should say, the beginning, that marks the beginning of this whole idea of probability. So in a sense, we've been learning how to count. The reason I'm learning how to count is so that we can directly specify the sample space. Now, once you have this idea of the sample space, and again, the sample space, I'll write this down later, is the set of all possible outcomes of an event. So when you get good at that, then these techniques as complementary counting come into play, and you're able to directly find the probability. Okay. So I want to piggyback off of this, and there's a problem similar to this in your homework. So let's say Paul flips, right? This is one of these flipping problems. So again, in probability, you're going to be dealing with coins a lot. We're going to be dealing with cards. So I don't know if you guys want to buy a deck of cards. If you guys don't have a deck of cards, Google deck of cards. Cards come up a lot, especially with probability. So Paul flips and dice, also dice. So you have dice, cards, coins, but we use cards a lot. Flips a coin 8 times. And how many ways can he flip at least 3 heads? Oh, do you want the Joker? No, we don't need Jokers. With the joke, without the Joker, it's 52 cards. So with the Joker, it's more than 52, 53. I don't know. Yeah, usually the Joker is not considered. So don't worry about the Joker. Unless the question, like the student says, specifies it. All right, so we have a problem like very similar to this in your homework. And yeah, so the idea is that we flip a coin 8 times, right? So okay. Eventually, what I want you to try to do is to visualize these things and identify what the event is, or what eventually what will be called the probability experiment. But for now, yeah, you can create a tree, but it's gonna be a lot of branches. So what I'm gonna do is this. First, I want to specify what is the event. So identify event. So what's my event? It's flipping a coin 8 times. That's the event. And then I'm specifying a particular kind of event, right? Or a particular kind of outcome. What's my particular outcome? I must flip at least 3 heads. So I'm specifying my outcomes. So these are specific outcomes. Specific outcomes of event. So my event is I flip 8 coins every time. I just flip a coin 8 times. Flip a coin 8 times. And then I want my desired outcome is for it to have at least 3 heads. So you can also use the word desired. Specific outcomes or desired outcomes. So let me call that an event. Call it A, right? So A is the set of outcomes that I'm specifically wanting, which is at least 3 heads. Now, what's an example of an object, or how would I specify one of the things that are inside this set? So this is when it gets a little abstract. So how can I consider an element in A? So an element in set A looks like what? An element just means a thing in A, right? An object in A. This is an object, this is the thing. that we're specifying, right? We're specifying that it's something that has at least 3 heads. So one way, right, is to list them out. So it could look like this, right? It could look like heads, 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 tails, 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 tails. That's many tails. No, I can literally say this thing right here, this thing is one of the outcomes in my set A. Right? You guys see that? And then another one. What would be another one? You can have the same thing. You can have heads, tails, heads, tails, heads, tails, 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 right? That. And then so on and so forth. Do you see how it becomes very, just even something as simple as this becomes very taxing to have to write this out again? Like there's a lot of them. Because if you see this event is when you have exactly 3 heads. This event here, when you have 8 flips, you also have 3 heads, but this occurs in different sequence, at a different time. So this one here is the first head, then you have the second one is going to be a tail, and then another head. Then you flip-flop in the first 3, but then you have tails at the end. And you start to see, oh, I can do this again. I can flip the order of the T's and the H's. Now it just becomes, you see, it just becomes an ordering of letters. But that's if you have 3 heads exactly. What if you have 4 heads? That's also included here, right? At least 3 heads means I have 3 heads, or 4 heads, or 5 heads, or 6 heads, or 7 heads, or 8 heads. That becomes, especially when the number of flipping of coins becomes like 1,000 and so on, this becomes very, very, in a way, annoying, right? So how do we take care of that? Instead of saying, hey, I want to know how many heads, how many ways I can get 3 heads at least, what do I say? You know what? It takes too long. How about the complement of A? What's the complement of A? It's not at least 3 heads. What's the complement of at least? Less. So it's less than 3 heads. Let's write it as 3 H's, right? If you're less than 3 heads, then how many heads is that? 0 heads? Or 1 head? Or 2 heads? Now, isn't this a bit easier? Because I have less cases. In the other one, I have 3, 4, 5, 6, 7, 8 heads. But when I consider the complement, I'm dealing with only 3 cases. Either you can have 0 heads, 1 head, or 2 heads, and that's it. Now, let's count that. So how many ways can I get 0 heads? How many ways is there? So let's just look at 0 heads. There's only one way, right? That means that all of them are what? So 1, 2, 3, 4, 5, 6, 7, 8. They're all tails. So what does this become? This kind of becomes like saying, hey, I have 8 spaces. And I want none of them to be heads. There's only one way. Do you see that? I'm not going to count. I'm not going to be writing out the T's and the H's. That takes too long. Do you guys see that? And then 1 head. What does 1 head mean? It means that the first is a head. And then we got T's, right? All the way down. But then what do you notice? Hey, another event, another outcome could have been what? Tails, heads, tails, 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 tails. Do you guys see this? And then so on and so forth. Like you can literally just drag the H and then you start to see that you can set up, you can count this, right? You can count this. And then instead of having to count it out and write it out, we just say, hey, I have 8 spaces and I want to select one of them to be a head. How many ways is that? As someone said, 8 choose 1. There's 8 choose 1 ways of selecting one of them to be ahead out of the 8. So then this becomes 8. And this becomes a lot easier now, right? Hopefully everyone is following. So 2 heads. I'm not going to do spaces anymore. It just gives you that just serves as a way to visualize it. But then now you start to see, oh wait, it just becomes, hey, I have 8 slots. And I want 2 of them to be heads. How many ways can I find the ways to get 2 heads, right? If I have this head to be this head and all of them are tails, that's only one way of doing it. Then I have to find another way to have 2 heads. So instead of doing that again, writing it out, I just say, hey, I just want to count them and do 8 choose 2. So what is 8 choose 2? We could do that really quick, right? 8 choose 2 is 8 factorial over 2 factorial times 6 factorial. This becomes 8 times 7 times 6 factorial over 2 times 6 factorial. The 6 factorials cancel. I'm left with 56 over 2, which is 28. I have 28 ways to have 2 heads out of the flipping of 8 coins. I mean, a coin 8 times after I flip a coin 8 times. Now, Christian says, is the answer 8 choose 0 plus 8 choose 1 plus 8 choose 2? That's the right answer to the wrong question. What's the question ask? How many ways can you flip at least 3 heads? And what did we find? We didn't find that. We found how many ways is it to not flip 3 heads at least? We found the complement. That's right. So this would be for the complement. So there's how many ways for the complement. So the number total number of outcomes for the complement is 1, or I can do 8 choose 1 plus 8 choose 2 plus 8 choose 8 choose 0, 8 choose 1, 8 choose 2, which is 1 plus 8 plus 28, which equals 37, right? So it's a total of 37. And then Fernando, that's right, Fernando. The usage of complementary counting requires you to figure out what's the total number of outcomes for the event. And what's the event? The big one that we identified from the very beginning. It's this guy. Remove this. Oops. So if I flip a coin 8 times, how many ways is that? What's the total number of ways? So the total number of ways, right? Total number of ways to flip a coin 8 times. And that's, well, again, there's 1, 2, 3, 4, 5, 6, 7, 8. There's 8 flips. How many choices do I have for the first flip? Either it's a heads or tails. Second flip, heads or tails, and so on. That's why all of these are 2. There's 2 ways to do it, which equals 2 to the 8th. The 2 to the 8th, if I'm not mistaken, is 1024, right? Could be mistaken for that. Oh, 256, pardon me. 2 to the 8th is 256. 2 to the 10th is 1024, so it's 256. There's 256 ways to flip a coin 8 times. So the idea is the following, and I'm gonna, before I do that, I'm gonna specify a definition here. So the sample space, write that. the sample space of an event is the set of all possible outcomes. And we use S to denote the sample space. And to continue with this example, I'm gonna do the following. So drawing here also helps. Right, Alexandra, that's right. So sometimes to just have a visualization of what's going on with things such as this, right? Flipping a coin, we draw a rectangle, and that rectangle is represents S, and that's the entire thing that can occur within this particular experiment, right? So flipping a coin 8 times, that's represented by this guy. And then this circle inside represents a subset, a smaller set within that sample space. And I'll call this A. So that's A. And then the shaded part, the outside of A, but within the sample space, all of this is called A complement. So everything that's not an A is outside of A. So then you start to see, wait, so A plus the complement is the sample space. So it makes sense if I figure out the number of things in the sample space and I subtract off the things that are in here, which is not in A. So if I take the total, subtract off the complement of A, I get the number of things in A. So then, which is what I wanted from the very beginning, right? So the number of things, or I should say outcomes, in set A is equal to the total number of things, or the total number of outcomes, which is considered the sample space, minus the number of outcomes in a complement. So then what's the total number of outcomes again? We just figured that out, 256. What's the total number of outcomes in the complement of A, which is the set of, which is the event, is a set of occurrences where out of the 8 coin flips, 3 of them are less than 3 heads. So you have 0 heads, 1 head, or 2 heads. That's 37. And then you do 256 minus 37, and you get 219. So a total of 219 ways. And this is your final answer. So the total number of ways to have to get at least 3 heads. Any questions about this? Is this fair? Is this straightforward? Everyone good with this? So we understand the sample space. That's a very important. This idea of sample space. It's the set of an event, or I should say probability experiment, but that gets kind of crazy. Is the set of all possible outcomes. Okay. So yeah, let me use, yes, someone saying something?
Professor, so You did find with the complement of A, but like, is it possible to find out directly without using the complement?
So you're asking me, is it possible to find it directly?
Yeah, that's right. Without
Of
like
course,
using the sample space and the complement.
of course. And I show that in that recording that I showed you. But I can just tell you how you would do that. So instead of saying, hey, the instead of counting the things in the complement of A, right, which is 0 heads, 1 heads, or 2 heads, I can do it directly. It's just going to take a little bit longer. I'm going to be counting the number of ways of getting 3 heads, and then 4 heads, and then 5 heads, and then 6 heads, and then 7 heads, and then 8 heads, and then 9 heads. I mean, not 9 heads, and 8 heads. I stopped there. So in a way, I can show you what that means. In a way, this is what I'm really doing. I'm taking 8 choose 0 plus 8 choose 1 plus 8 choose 2 plus 8 choose 3 plus 8 choose 4 plus 8 choose 5 plus 8 choose 6 plus 8 choose 7 plus 8 choose 8. And this is all equal to 2 to the 8th. So this here this is the number of outcomes in A complement. This is the number of outcomes in A. And this is the total number. So you can directly compute it. You just have to compute 6 computations. And the complement just requires 3. So it's whatever floats your boat, really, at this point. If you want to do this, then go ahead. By all means, you can do it. It's just sometimes it's easier. It's just less work to do the complement. That's all. Okay. So does that make sense?
Oh yes, Professor. Thank you.
Yeah. Now, there's a few things I want to go over really quick. So we've done a lot of counting. I'm going to continue to count, but now we have a different context. Now we're going to be dealing with probability. Okay. And we talked about sample space and events and the complement. So this is important. We have 3 axioms of probability. Now, an axiom is sort of like a definition, but we just hold it to be true without any further evidence. So these are like the pillars of the theory of probability. So once we have these established, then everything else kind of builds upon it. So an axiom is something we hold to be true without much resistance. We just accept it. So the first one is the following, that the probability of any event, so we start using a lot of notation now, right? So this is saying the probability of an event. Probability of any event. So I don't care what the event is. So E represents event. And P, of course, is the probability. So you can consider as we'll start to consider probability almost like a function, We're taking a probability and we're taking an event, we're inputting it to figure out the probability, and it's going to spit us out a number. And that number has to be between 1 and 0. So if you get a probability of something and it's negative, then something's wrong. And if you're doing something, if you get a number bigger than 1, something's wrong as well. So the probability of an event has to lie between 0 and 1. It could equal 1, equal 0, but it can't go beyond 1 and it can't go beyond to the left of 0. And that makes sense, right? So sometimes people relate probability with percentage. So you kind of consider that as the percentage of something happening, right? Is either it's never going to happen, 0% of chance of something happening, or 100% chance of something happening. And that's kind of how probability is related to the way we sometimes consider things happening, right? We consider there to be a 40% chance of something happening, which is the same thing in probability to say the probability is 0.4. Okay. So think of probability as the decimal version of percentages that we use to count, to establish chance. The second thing is that the probability of the sample space is 1. I know that's kind of weird to say. So remember, S represents sample space. What this is saying is a bit redundant, but it's like saying, what's the probability of, it's like saying, what's the probability of something in a sample space occurring? Well, because the sample space contains all possible outcomes, for sure one of them is going to occur. It's sort of saying that. So if I have a sample space and I want to find a probability of my sample space to occur, which means what's the possibility that one of the possibilities occurs? Well, if I'm telling you all of them may occur, then one of them is going to occur. Again, sometimes these axioms we just accept as part of, but it's important. Okay. Any questions about that second axiom? So the first axiom is the probability of any event within the sample space is between 0 and 1. The probability that something occurs from the sample space is 1. And then the last one is the following. So E. So we're going to be using like indices for this. So let E sub I be an event of an experiment, or I should say a probability experiment. So we have like E1, right? So examples of that is E1, E2, all the way to the En. Let's say, right? And one thing we're going to start, I mentioned this before, but we're going to be speaking about is mutually exclusive events. And suppose all EI, all events, I should say all events, E sub I are mutually exclusive. Now, what does that mean? Let me give you an illustration of that. So again, I'm gonna draw a rectangle, and this rectangle represents a sample space for some kind of experiment. Then I'm gonna draw sets, and these are the E1s that we're speaking of. So we have set one here, right? Oh, let me draw this better. So we have E1, and I'm gonna draw these as sets like this: E1, E2, E3, dot dot dot, En. So I'm gonna call this E1, E2, E3, E sub n minus 1, and E sub n. Now, with these sets, we don't add sets. So the operation for sets is, if we want to combine sets or unite sets, we use what's called union. So if I want to take the union of these sets, right? So we call something called the union. So let me define that. The union is denoted by this like a U. It's just uppercase U. And it represents the combining, or I should say, represents the set that contains everything from each set. So, for example, I can take E1, I can union that with E2, I can union that with E3, and then I can do that so on and so forth, right? E sub n minus 1 and union E sub n. What I'm saying is I'm including all of these guys together and I'm creating that as a new group. So instead of writing this out like this, E1, E2, E3, E sub n minus 1, E sub n, I can do the following. I can write it as this, a big U, right? I do E sub I, and I goes from 1 to n. It's kind of like the summation notation, if you guys ever seen that. We'll see that, like the summation notation. The indices start from a certain number, and then they counter all the way to the top limit here. So I'm literally, when I'm saying this, is I can just specify this as a shorthand notation. So when I have mutually exclusive events and I want to figure out, so I haven't even talked about the third, the notation for the third axiom yet, but the probability that I have a union of mutually exclusive events, the probability of the union of these events occurring is equal to the probability of one of them occurring plus the probability of the other one occurring plus the probability of so on and so forth. So instead of writing that out, right, instead of writing this is the probability that E1 occurs plus the probability that E2 occurs plus all the way to the probability that En occurs, instead of writing out all the sum, I can use shorthand notation. Summation notation. So what I'm saying is the following. Consider these mutually exclusive events as one single group when you bundle them up. The probability that this bundle occurs is equal to the probability that one of them occurs, plus the probability of the other one occurring, plus the probability of the other occurring, and so on and so forth, all the way to the last one. Does that make sense? Sometimes all of this letters, right? You could get lost with the letters and be like, wait, where did the E come from? But that's why it's useful to draw things out. And look, we're drawing little rectangles and circles. Okay, so these circles represent sets, and a union of sets, the probability of a union of sets occurring or event occurring is equal to the probability of those individual events occurring. And that's the third axiom. Once you have these three axioms and you take them as true, you have this whole field of probability opening up. Okay, so again, this is where the theory comes just as a wave, and then hopefully with some examples, it makes a bit more sense. Now, one thing I should say, and sometimes whether you do this in the beginning or in the end or afterwards is the question. But the question is, what is probability? How can we define it for now? For now. So I'm gonna say this is definition for now. So the probability of an event is defined as the following. So it's the probability of an event is equal to the number of ways that event E occurs divided by the total number of outcomes. And the total number of outcomes specifies the sample space. So that's the probability of an event. We find how many ways this specific event occurs. We count them. And then we count the number of ways that the sample space, what's the total number of ways of just the event, the experiment occurring? What's the total number of outcomes that this experiment has? When you find that number, you divide it, and that will give you the probability. So that's the first way we're going to define it, because there's a more general way to define it. But then once you have this, you start to see, oh, probability is just an application of counting. It's just like the next step for counting. So for example, now let's look at the examples. We'll start slow. What is the probability of rolling a prime number when a fair when a fair six-sided dice, or I should say die. Oh yeah, die is rolled. And this is important to say. Fair means that every outcome is equally likely, right? So fair means each outcome in sample space is equally likely. So the question, Amir, what is prime? So we'll talk about that quickly. First, I want to specify though, what's my S? What is S? S is 1, 2, 3, 4, 5, 6. Remember, S represents the sample space of the experiment. What's the experiment? It's rolling a die. So this is my experiment. I'm rolling a six-sided die. And so that represents the sample space. And then what am I considering? What's like the specific event that I want? This is the specific event. I want a prime number. I'm gonna call this A again. It's not too creative. We call it A. So A is what? The event that I roll a prime number. What does prime mean though? What does it mean to be prime? A prime number is a number whose factors are only one and itself. So the prime numbers in the numbers 1 through 6 are going to be 2, 3, and 5. That's right. So this is simple, I know, but I just want to make sure we get the simple parts down and clear. So then what are we looking for? What's the goal of our question, or what's the objective? The probability of A. That's all we want, right? This is our goal. So what's the probability of A? What's the probability of rolling a prime number? Well, we count the number of ways to roll a prime number. In other words, count the number of things or objects or numbers that are in the set A. There's only 3 of them. So again, it's not this 3, I just want to make sure this 3 is not the same as this 3. This 3 is the prime number, which is the outcome of that we want. This 3 specifies the number of things in the set, in the space that we're considering. They're not the same 3. And then how many ways are there? What's the total number of ways for this to occur, for this experiment to go? There's 6 ways. So obviously there's 50% chance, right? 0.5. There's a 50% chance that when you roll a die, you're going to roll a prime number. Simple as that. But of course, we like getting a little bit more intricate, a lot more intricate, I would say, when we talk about cards. So consider a 52 card deck. Find the following. So I'm gonna give you a couple things here. So make believe you have a deck and you want to find the following. You have a standard deck and it's just on top of your table. And what's the probability? Find the following probabilities. At the top card is a heart. So you have to understand the organization of a 52 card deck. You have 4 suits, right? We talked about this, 4 suits. You have hearts, you have diamonds, and then you have clubs, and then you have a spade, right? So how many hearts are there? And we divide the 4 suits up equally. So there's 13 cards for each suit. So how many hearts are there? So I like making this clear. Like the probability top card is a heart. So what's the number of ways of getting a heart? There's 13. 13 hearts, right? And then how many total cards are there? What's the total number of ways of selecting that first card? There's 52 ways. So a fourth. Does everybody see this? What's the probability of that the first card is a heart? Well, it's only 25% chance, right? Since a fourth of them are hearts. Makes sense. What's the probability that the top card is a face card? What does face card mean? It could be a jack, a queen, or a king. So how many jacks are there? Well, there's a jack for every suit. That's 4 jacks. How many queens are there? Well, there's 4 queens. There's 4 queens because there's a queen for every suit, and so on and so forth for kings, right? So 4 times 3 is 12. Are you guys following this? Is a jack, queen, or a king? Well, there's 12 of them out of the 52, and then we always try to reduce. always try to reduce as much as possible. So you can divide this by 4, and you get 3 out of 13. And whatever that percentage, whatever that decimal is, that's gonna be the percentage, right? And so if you do that, it's gonna be believe yeah, a repeated decimal. So it's approximately 23%. So this is approximately 0.23 dot dot dot, which is approximately 23%. So 23% of the time, you're gonna get a jack, king, or a jack, queen, or a king when you select one card out of a deck. Make sense? Next one. Now we're gonna introduce us something else. What if the top card is red and second card is black? So black indicates what? A black card is either gonna be a club, I know this is green, but or a spade. And a red card is gonna be either a heart or diamond. So what's the probability that the first card is red? Well, now we start to see using these slots things that I like. How many red cards do we have? We have 26, right? Don't we have? So this is going to be red card. This is going to be black. So be careful here. Now it starts to get a little bit more complicated. There's 26, aren't there? There's 26 red cards. And then how many black cards are there? So make believe the first card was red. And then the next card is black. How many ways is that as well? 26, right? So what's the total number of ways of selecting a red card and then a black card? Or what's the total number of ways of getting a card, right? That's red and then black. There's 26 times 26 ways. So that's the numerator. This is going to be in the numerator. What's going to be the denominator, though? What's the total number of ways of selecting that first card? 52. But then once you select one card, there's one less card to choose from. So you're going to have 51. Do you guys see that? So then what's the probability then? That first card is red, second card is black. It's 26 over 52 times 26 over 51. And of course, you can multiply this out. You can use your calculator, so on and so forth. But I hope you guys can see that you can simplify things. Try to simplify your fractions. 26 out of 52 is really what? A half. You guys see that? And then, that's right. And then the 2 goes into 26 13 times. So the final answer is 13 out of 51. That's my probability. The probability that I'm selecting two cards, the top card and the second card, right? The probability that of that experiment, I get the first one red, the next one black, there's a 13 out of 51 chance of that happening. And how do I figure that out? Well, there's 26 ways of selecting a red card if I want that. And there's 26 ways of selecting a black card. What's the total number of ways of selecting the first card? There's 52 possibilities. After one is taken away, how many do I have left? There's 51 possibilities. So you multiply the two numbers here to indicate the total number of ways of selecting a top card and a black and a second card. And this number here represents the total number of ways of getting the top one red and the second one black. So then we see how we're kind of differentiating these numbers. They're not just numbers that we're multiplying. They're representing very specific outcomes, very specific events. Okay. Any questions about that? Okay. Um, let's look at the last one here. What's the probability? Chaitanya. Yeah. Yes. The probability, I think I said this in the beginning. Probability is probably one of the most, and I was told this by a professor when I was in college, telling me the most important thing. Yeah, you can do this in Vegas. Yeah, exactly. There's a whole movie on this called, I think, 21. Well, they're like this guy from MIT. He's a student. He's like a wizard, and then he teams up with the professor, and then they literally try to take on Vegas. Um, of course, the house always wins without giving any spoilers, but you can count cards. But the idea is when you, for example, if you guys ever seen poker being played like professionally on ESPN, I don't know if they do that anymore, but they used to present their poker tournaments, and percentages comes up of the possibilities of a card that you want to appear. And how did they do that? They don't just willy-nilly to say, oh yeah, there's 28% chance that you get a heart. No, this is cold hard mathematical fact, and you can compute them yourselves. How do you play poker? You know what? I have a friend that plays poker, Texas Hold'em. I never actually learned it with him, but there's different variations of poker. But I know it's a 5 hand card. It's a 5 hand thing. It sounds complicated when they explain it to me, but I never played it myself. But the idea is that with this involved, with this mathematics, you can compute computate. You can compute ways of getting a full house. You can compute ways of these things happening. Yeah, so the probability is very important, especially now, especially in the world that we live in. So what's the probability that the top 2 cards are both aces? So I want the top 2 cards being an ace. So then how many aces are there? Well, there's only 4 suits, right? So we can only count them. There's only 4 ways. So the first card is an ace. So first ace, second ace. Well, the first one has to be an ace. And then the second one has to be an ace. But once I select the first ace, there's only 3 left, right? And then what's the probability? So this is the numerator, guys. This is the numerator, right? This is what I want. The outcomes that I want, the desired outcomes. Now, what are the total outcomes? That's the denominator. It's the same idea. We have 52 ways to select the first card, and then we have 51. It's the same idea. Hopefully, you start to see the chances of this happening is much smaller now, right? 13 out of 51 is what? Let's see. It's around a 25% chance, which is not great, but it's not terrible. Now try to do this. Probability of the top 2 cards being aces. That's 4 out of 52 ways times 3 out of 51 ways. 4 out of 52 reduces to what? 1/13 times 3 out of 51. And then 13 times 51 is 663. So this is the chance. And then you can reduce this further because 3 goes into 51 17 times. So this is 1 out of 17 times 1 out of 13. So when you multiply that, 221. So the possibility of you getting the first 2 cards, yeah, thank you, Chaitanya. The probability that you get the first 2 cards being aces, it's 1 out of 221. And what that would be in a percentage would be 0.0045. So this is roughly 0.0045 ... which is approximately 0.4%. So you can actually like compute this in real time. So I have less than a 1% chance of getting the first two cards being aces. So it's very unlikely, right? It's very unlikely that this occurs. Then this is when the idea of chance comes into play. So what do you guys think about probability so far? I think this is when things start to get a little bit more interesting. And these are the problems that you're going to be dealing with. Now let me see if I have one more kind. So any other questions? Will you be here at 12? Yes. Yes. So again, for those of you who need more help with the homework. Oh, yeah. Let me just tell you that ticket problem with the punching of the holes, there's nine numbers, or it's in a grid, 3x3 grid. That question is really nice. It's a really nice question. It's probably the hardest one out of all the 10, but it's a very, I would say, even beautiful question, a problem, because of what's expected of you. And I guess let me just briefly indicate what's going on, right? So we have a 3x3 grid. We have beautifully hidden frustration. Yeah, I know. That's the whole point. That's what math does to you. So we have this, right? And then the wording of it is a little strange, but your numbers can be different. Some people have 2 holes that they punched in. Some people have 3 holes, 4 holes, right? So let me just stick with 3 holes. So let's make believe you punch 3 holes in, right? And it's a weird ticket, and they're talking about this arrow, right? They're talking about an arrow. It's just a weird, strange scenario. So you punch 3 holes. Let's just punch 3 holes. So I'm gonna indicate that with something like this, right? I punch 3 holes. What they're saying is you can flip that ticket and it still be valid. So when I flip it, what does that mean? I'm gonna try to like recreate this, right? So if I were to flip, like literally take that and then just flip it over on itself. If I flip it and then if you see it, my arrow would be here, right? My arrow would be on the other side. And I can't write backwards, so I'm not even going to try to do that. But you can envision that when I were to flip it, the 1 is no longer going to be here. The 1 is going to be on this side, right? If you see that, if I flip it, this will be 2, this will be 3, this is 6, this is 5, this is 4, this is 9, this is 8, this is 7. Do you guys see that? And if I were to flip it, the holes would not look like the one I originally have. If I flipped it on this axis here, if I flip it on that axis, I would have this instead. I would have the 1 here, the 6 here, and the 8 here. What they're saying is that these 2 tickets are the same. So the holes have to be 2, 5, 8 along the vertical axis. Oh, see, you start to see that, right? So then what's happening is, if this is the case, that these 2 things are acceptable, then that means that the one that looks like this, if I had this right side up, I'm just gonna use a different color for now. So if I have this to be right side up, which is 1, 2, 3, 4, 5, 6, 7, 8, right? 9, and then you have this arrow here, right? If I have this right side up, then what they're saying is that this is also valid. It will be 3, 4, 8. This. What they're saying is that this is equivalent to this. They're both the same thing. So in a way, these numbers start to become irrelevant. The numbers are irrelevant. if we're saying that this is a valid, right? This is a valid punching of holes. You flip it, you get this one. This is the same one, and they say this is also valid. So that means that this one here is essentially the same thing as this. They're the same. So there's this idea of overcounting. So the idea is this. I'm just going to give you the idea. The idea is find the total number of ways. If you have the 3-hole version, you can have the 2-hole version, you can have the 4-hole version. It doesn't matter. You just replace the number. Find the total number of ways of punching the number of holes that you need. So if you have 9 numbers, what's the total number of ways of punching 3 of them? Well, there's 9 choose 3 ways, right? So 9 choose 3 ways is all the ways you can punch 3 holes just randomly. Of those 9 choose 3 ways, there's going to be a variation that repeats itself. In the 9 choose 3 ways, this and this combination are different. But for the problem at hand, they're exactly the same. Do you guys understand what I just said? So then I think Alexandra brought this up, right? You said, so you have to find the numbers, what is it? Along the vertical axis, 258. That's right. There's going to be some, you have to count, there's going to be some of them that when you flip it, right, it's the same thing. So for example, 258, if I flip it, there's only one of them. If I do this, 456, there's only one way of doing that. Because when I flip it, I get the same exact thing. Does that make sense?
So I have to divide by 2?
So you have to be careful. Yeah, no problem, guys. If you guys need to go, you guys can go. I'm just giving you guys like a little like help with this one because this is a very nice one. This is a very nice problem. So you do have to divide by 2, whoever said that, but you have to do it carefully. You don't divide by 2 after you do 9 choose 3. You don't do that.
How do I find the ones where they're not symmetrical? Do I have to write it? Do I have to list them up? That's a real question.
No, that takes too long. The number of the ones that are asymmetrical are more than the number of ones that are symmetric. The idea is to find the ones that are symmetric. So this is a wonderful problem because you have complementary counting embedded in it. So what's the entire set sample space is punching 3 holes into 9 numbers, 9 spaces, 9 boxes, right? Punch 3 of them in. That's the sample space. Find the ones that are symmetric. So the sample space is divided into appearances where they're asymmetric and symmetric. The symmetric ones are the ones that you want to take away from the total. So if you take away the symmetric ones out of the total, what are you left with? You're left with the asymmetric ones. But each asymmetric one has a copy, has a doppelganger. So that's where you divide by 2.
I would have thought that I divide the symmetric ones by 2, so I only count them once.
No. If you divide the symmetric ones by 2, you're implying that there's more than one symmetric one when you flip. What I just showed you with this simple example, right? I showed you that 168 is the same as 348. Why are they the same? Because if I flip this, right? If I flip this guy, I get this. Not in terms of the numbers, but in terms of the spaces that are punched out. If I flip this, I get these spaces here being punched out. Does that make sense? I'll stop with the recording.